In this video, we're going to take a look at some issues around accident period hetero. Now, in the normal course of things, we regard this as fairly rare. You have development period hetero, and this corresponds to, I think, a fairly normal experience with loss arrays, which is that as you come to later in the development cycle, you tend to have fewer claims, but the range of claim sizes is different simply because they're late claims for various reasons. So one would expect changes in the variance of the claim sizes to occur with along the development direction. In the accident direction, although one doesn't encounter this, it might be more usual to put it down to a change in the mix of risks being written. And if the change is large or significant, then we would usually recommend a different way of proceeding. So just as an example, let's just move to our screen here. Let's say that we had a, this is our loss array, and we have our accident direction here and our development direction here, our calendar direction out there. And let's say that there was a change. So this was picked up in perhaps an accident year hetero change. We'd noticed that along the accident direction there was a change in the volatility in the variance of the risks we were getting, and we could split the triangle in this way. So what we might ordinarily do is say, well, there's been a change in the mix of risks here, and so although there may be something in common in the development direction, when you look along the calendar direction, which is out here, it could well be that each of these two risk classes actually responds to the inflationary factors, the calendar year factors, in a different way. So it would make sense to split the triangle into two portions, one of them containing the upper portion and the other containing the lower portion, so we have the same split here. But in the first case, we put all zeros here, and in the second case, we put all zeros here. And then we model the two triangles separately, but put them together in MPTF. So by doing that, any information that's shared, that's common between the development decay patterns, would be shared between the two arrays, but they could have individual accident levels and individual calendar year trends, or possibly some sharing of information in calendar year trends, but the calendar year trends not exactly the same. So that's the more typical experience. However, we do have this facility for accident year hetero, and it can be of use. So as an example, we're just going to go through how this works. So let's start here with our triangle group ABC. And what I'm going to do is I'm going to create a transpose of this particular triangle, PLI triangle. Here it is here. And then I'm going to model it and show that how, when you transpose it, everything that occurs along the development direction on the original triangle occurs along the accident direction in the transposed triangle. And so the effects of doing development hetero in the original triangle will be come out to be precisely the same as doing accident hetero in the transposed triangle. So let's, to begin, see how we can create a transposed triangle. So I start from this triangle, and I'll go here, right-click, and copy all. So I've got the entire contents of this triangle stored in my clipboard. Then I'll go back to the Triangles tab here. I'll create a new triangle, which I'll call PLI transpose. and I'll open this. It'll initially come out empty. Now before I paste the new data in, what I'll do is change the view to transpose it. Instead of accident by development, I'll change it to development by accident. Then I'll paste those numbers back in, and then I'll change the view back again to accident by development. And then I'll save this. So now if we look at the two triangles side by side, there's my original, and here's my transpose. I do this? No. There are the two. Yes, now I've got them side by side. So here we see in the original triangle 153, 188, 134, and those same numbers 153, 188, 134 are occurring down here in the accident direction and in the second triangle. Okay, I'll shut those and go back to this view. Now we have a data set PLI, and automatically we have a data set PLI transpose. These simulated triangles, we actually don't need those. I'll remove those. Just to clean things up. And later on we might accumulate this transposed triangle, but let's look at it in PTF first. So now let's open the two data sets in PTF. And let's start out by putting the two model displays side by side. Now these model displays look different, and of course they are different. Everything that's on the development direction in the original is now on the accident direction in the transposed. But the SGI trend, so the SGI model, which begins with a single accident year level and one trend in the development direction, one trend in the calendar direction, this model looks quite different. In fact, if we look closely, we can see a number of things that they have in common. The accident year levels 12.1906 in the transpose, 12.19. So the accident year levels are exactly the same. The development year trends are precisely the negative of each other. This is 0.3845. This is minus 0.3845. The calendar trends are different, and it's not immediately clear how they're different. So let's have a look at this and see why we're getting these trends showing up the way that they are. So I'll move back to my drawing pad. So if I begin with an array like this, and it's an SGI array, so I have, I'll call it G is the development trend. It's an SGI model, so there's a single gamma, G is my gamma, and I is the calendar trend. So what's the trend that we're experiencing along a development direction, along this horizontal direction? It's not in fact G. The resultant trend along the development direction is G plus I. Because remember that the calendar year trend projects onto both the development direction and the accident direction. And so the actual trend from cell to cell as you move horizontally, it's moving step by step with a G, but then each time you move one step to the right, you also have moved one step in the calendar direction, so you get the I added onto that. So you get one step of G and one step of I. In the accident direction, although the model looks flat, there's no change in accident levels. In fact, from year to year along the accident direction, because each year you're actually on a different diagonal, you're going to get a resultant trend of I. So these are the resultant trends. So in my transposed triangle, this is the transpose, I want the trend in this direction to be G plus I, and I want the trend in this direction to be I. So if I use small g and small I for the G is the development and I, small I, is the calendar. If these are the trends in the SGI model for the transposed triangle, then the equation I want is that small g plus small I should equal big I, because that's the resultant trend along that horizontal direction, and the trend down here, which is I, little I, should equal G plus I. So when we put these two equations together, we can actually solve them for small g and small I, and that gives us small g plus big I equals big I. And so that immediately tells us that small g is the negative of large G. And again, we have that small I is G plus I. Furthermore, if we reverse this, let's say we knew small g and small I, and we wanted to find large G and large I. Well, large G is just the negative of small g, and large I is small I minus large G, which is small I plus small g. So we can see that the relationship, as it ought to be, is entirely symmetrical between the two, and that is in fact the relationship that we see here. The G trends are the negatives of each other. When you add this trend, the 0.3845, to the minus 0.2851, you end up with this trend here, the calendar trend and the transpose. And similarly, if you add this and this together, you end up with this. So the point of all of this is that these are precisely the same modeling surface, they're just viewed from different angles. And the fact that these two extant levels are the same, the extant level on the log scale means that the average of the logarithms of all of the entries in the data array is equal to the average of the average level in the model. So since that's based on the average of the elements in the entire array, it doesn't matter whether the array is transposed or not. The same calculation is going to produce that starting extant level. So now if we turn to the residual displays, we can see that in fact they are identical but transposed. The shape that we see here in the extant years in the transposed is precisely the shape we see in the development years in the original data. So now let's run a chain ladder model for each of these. Oh, no, sorry, this one here. This one here. So I've right-clicked on the list of models, and I'm going chain ladder and chain ladder for this one. Oh, I didn't get the chain ladder for this one. So now I've run the chain ladder on both, which means one parameter in each development year and one parameter in each extant year. And again, you can see that they're perfectly symmetrical. We have exactly the same pattern here along the development direction, as we see here along the extant direction. You can see these look exactly the same, whereas this shape here is exactly the same as the shape here. The pattern along the calendar years is then identical. If you click on an individual point, it will be identified as coming from a different place. So this little point here is on the transpose is extant year 1977 development 4. On this one, it's extant year 1981 development 0. However, it still corresponds. It is the same number. It's just placed differently in the triangle in the two different cases. So now let's see what happens when we put in some heteroskedasticity. Let's begin with the original data. And we'll go up here to the heteroskedasticity analysis tab. And this time I'm going to put extant year hetero in the original data. So I go up here to the manual. And then I click this tab, extant hetero, and I get the picture, the extant year picture from the residual plot there. So I look at this and I say, well, the variance here looks a little bit bigger than the variance was before, so I'll put a parameter in here. I put that parameter bar there. Then I fit the variance parameter. And it does find a difference between the two. However, the difference is diagnosed as being not statistically significant. Since this is just an exercise, I'm going to go ahead with this one. But before I continue with that, let me just do the same experiment on the transposed data. But this time I'm going to stick to the development direction, and I'll put the same parameter here. And I get precisely the same. Let me just put these together. I get precisely the same picture, even though in this direction it's development year hetero, and in this direction it's extant year hetero. So I'm going to apply the two of those, and then go back to the model displays. So in the model displays, again, here, I should have shown you this before. We noticed that, in fact, we have exactly the same parameters in both models, but they're transposed. The extant year parameters in the transposed, for the transposed data, are exactly the same as the development year parameters for the original data, and vice versa. The heteroskedasticity that we just performed appears in the development direction in the transposed data. You can't see anything in the original data because we don't show extant hetero on the graph. We indicate the presence of extant hetero by these two asterisks. So now these are the same, but these are the same model, and you can actually see the effect of this by looking at the, let's look at the variance array here. So this is the transposed data. This has development period hetero, and you can see that the variance is 0.0442 up until period 5 when it changes to 0.90979. We can also get the variance to periods list, and we can see again this change that's occurring in the development year direction here. Now when we look at the original data and we pull up the same variance array, what we're going to expect is to see that same change, but now occurring 442 to 979, now occurring in a horizontal cut in the triangle. Now when we forecast with this, we're going to forecast all the cells in this white region here. When we forecast with the original data, the forecast cells are going to pick up the variances from this array. So they're going to follow the same pattern. I mean, probably easiest to see if we look at the forecast. I think I'll just click these just so I can get access to this picture here. So This one is the original data. No, this is the transposed data, because this has the, no, sorry, this is the original data. This has the accident year hetero in it. So the ratio is that the hetero, the variance jumps by a factor of 2.2 after 1982. So the cells there have a larger variance. Also, the data that was in those cells contributes less to the determination of the parameters, since it's being treated as having a higher variance. But we can see that in the forecast that these cells here along these accident periods will have the higher variance than these. If we look at the same, I'll shut this one down. If we look at the same table, this is the future variances table for the transposed data, which has the development year hetero. We can see that this factor of 2.2 comes along here. And again, here, all of these cells are the ones that are going to have the higher variance in the forecast. Now, they're precisely symmetrically opposite each other. So what we expect when we do these forecasts is that the two means are going to come out to be exactly the same. So I'm now going to run both default forecasts, and then we can get to these. Oops, I meant to do this. And so let's take a look at the two forecast summaries. And we see that the mean and standard deviation is identical in both cases. However, you'll notice that the numbers in the column here, the outstandings by accident year, are different in the two cases. Interestingly, the one for the original data, the numbers here go from very small to quite large to add up to this 5 million. And that's the usual thing where the first accident year that actually has an outstanding, which is the second accident year, only has one cell at the very right-hand end of the array. This has two cells at the right-hand end of the array. So these numbers are already small. You may recall that our model, it's up there, has a significant development decay. So whereas in this one, in the transposed version, the cells here, this one cell here really corresponds to something like the first cell. And what is it? It's the it corresponds to the early cells. So what we're finding here is these numbers are much more equal to each other, because the and this is a sum. Well, it's a little hard to express, but I suppose it's easier to see if we look at the contrasting model pattern and notice that here in the development direction, the numbers go up. So we're going to get large numbers at the end of the development. And in the accident direction, the numbers are going down, so that at the end of the forecasting array of the lower cells, we've got the smaller numbers all along that horizontal, but more of them. Whereas at the top, we have a smaller number of numbers, but they're larger. So it's just an artifact that we get this more balanced set of numbers. We can also look at the two forecast tables side by side, and as expected, the numbers in these cells are in fact just the transposes of the numbers in these cells. So where I have 14,653, 17,305, this is in the last development period as I run down accident years in the original. These numbers here turn into the last accident year as I run along development in the transposed. So that again is another reason why the sum of all of these, a large number of small numbers added together, is less out of balance with the number here, which is a small number of large numbers added together, than what you get here, which is a small number of small numbers as compared to a large number of numbers, which includes some very large numbers at the bottom. So anyway, all in all, the two ways of analysing the data are quite consistent. The accident year hetero works in exactly the same way as development year hetero. It just happens to be in the accident direction. So now I'm going to turn to having a look at the cumulative version of the same array, the same loss array. We'll look at the cumulative of the original and the cumulative of the transposed, and see what we can conclude out of that. So to begin with, I'm going to close all of these PTF models, so I don't need to save these. And let me restore my triangle group here. So I have a cumulative of the incremental. I'm now going to create a cumulative of the transposed. Now the cumulative of the transposed is not the transpose of the cumulative, because we're adding up different things. The sum, well, obviously the sum of all the elements in these is the same as the sum of all the elements in these. Well, no. But, well, that's not quite right either. But the sum, if you add up well, the sum of the incremental and the sum of the transpose to the incremental is identical. But in the cumulative, no, that's not going to be the case, because relative to the original incremental, the difference is the standard cumulative we're accumulating horizontally, so we're taking the 153 and we're adding it to the 188 to produce the number in this position, then we're adding on 134 to produce the number in this position, and so on. When we transpose when we accumulate the transpose, we're actually adding together different numbers. So along this top horizontal, we'll be starting with 153,638, but then we'll be adding on this number, and then we'll be to produce the number that's there. Then we'll be adding on this number to produce the number there. So the array will be quite different. However, if we open both of these in, so we're about to open these two cumulative data sets in ELRF, but before we do it, really we need to compare them on an equal basis, and I've just noticed that one of them has an exposure vector associated with it, which I need to remove so that they're both on the same footing. The exposure vector, of course, works along the accident direction, so I don't really have a symmetrical equivalent to that to run, so I can only do these transpose comparisons in the absence of an exposure vector. So let's open ELRF on this one, and then open ELRF on this one. Put those two side by side. Well, we can see the ratios here. And of course the ratios are completely different. If we look at the residual plots, similarly they are quite different. We don't have the kind of symmetry that we had before. The accident pattern here is not the same as the development pattern here. However, when we run the forecast, and let me do this and then this, so put the two forecast tables side by side. That's the forecast table for the original data. That was the original data accumulated. And I get a forecast of 5277760 with a standard deviation of 152246. In the case of the transpose, when I do this, I get a mean of 5277760, exactly the same number, however a standard deviation which is different. So let's see if we can understand why this has happened. So we're running ELRF in the default model, which is the MAC model, which is basically the standard chain ladder where the development factors are the volume-weighted averages of the respective development years. And what we find is that with these two quite different cumulative triangles, the numbers in the triangles, let's go back to these, numbers are entirely different. They're not. These are not the transposes of each other. Let's put the two tables up side by side. That's the transpose table. To get the forecast. Doesn't work. I just have to manually put these two side by side. So here they are. Here's the original data accumulated. Here's the transposed data accumulated. And these two arrays have, in fact, very little in common except this top element here. They're not the transpose of each other by any means. So they're quite different arrays, and this one seems to have larger numbers, much larger numbers than this one. Oh, to some extent. Not altogether. But at any rate, what we found when we ran ELRF here and we looked at the two, that was the two forecast tables side by side, forecast table for the original and the forecast table, forecast summary for the transpose, that the means turned out to be exactly the same. There is a reason for this, and the standard deviations turned out to be somewhat different. So let's see if we can understand the reason for this. Let's go back to our drawing pad here and start a new page. So let's begin with a picture of an incremental array. So this is incremental. Now I'm starting with an incremental array because what I want to do, my intention is to complete the array, and the numbers that go in the forecast portion of the array here, these are incrementals, but when I add them up, so the sum 1, sum 2, sum 3, these numbers here are going to be my outstandings. The sum of the incrementals in the forecast portion of the array. So these numbers here on the left-hand side are all the known numbers and the numbers with these horizontal stripes of the forecast. So what I'm going to look at is, let's draw it like this. Let's say we have a number in a cell here, and this is one of our unknown numbers, and let's see how this number is calculated using the volume weighted averages system. So this is an incremental, but what I'm going to do in order to compute this using volume weighted averages is I'm going to add up all the numbers to the left of it until I get the total in fact of all the numbers on the left, which sits immediately to the left of this box. And then I'm going to multiply this number by a ratio, which I calculate by looking at the relationship between these numbers and these numbers. So I'm going to multiply this number by that ratio, and then in order to get the incremental that sits in that box, I'm going to subtract the result. Subtract this number here, the total of all the previous values, from the product, the new cumulative that I find here. So if I just call this area here area 1, and this area here area 2, and this area here area 3, and if I make the convention that if I put brackets around a number, what I refer to is the sum of all the numbers in the region that has that sum of all the numbers in the region that is labeled in that way. So the development factor that I'm going to use to produce the cumulative in this box here, the cumulative corresponding to this box, development factor is the ratio of the sum of all the elements in this column here, all the cumulatives in fact in this column here, with the ratio with all the cumulatives in the immediately preceding column. But if you think about it, the development factor is, by this token, is actually the ratio of 2 plus 1 over 1. And why is that? That's because the sum of all of the elements in the cumulative that belong in this column here is in fact just the sum of all the numbers in the incremental table in the region that I've called region 1. Because as we add up each row, we get the elements in this column of the cumulative are just the sums of the rows. And then if I add up the sums of all the rows, I get the sum of the entire rectangle. Similarly, in the cumulative array, if I add up all the numbers in the column corresponding to the part I've labeled number 2, then those numbers are going to be the sum of all the numbers in this region together with all the numbers of this region of the incremental table. So the development factor turns out to be this, and so the cumulative in, I'll call the box X, cumulative in X equals 2 plus 1 over 1 multiplied by 3, 3 being the number that sits immediately to the left of the box labeled X. In other words, the cumulative immediately to the left of that. Now this is just 3 plus 2 times 3 over 1. And so the incremental in X is just this quantity take away 3. So that's 2 times 3 over 1. And the point about this quantity here is that it's entirely symmetrical. It doesn't matter whether you're doesn't matter which direction you're looking in, whether you're looking horizontally from left to right or whether you're looking vertically from top to bottom. This incremental number will be exactly the same. So when you're conducting the chain ladder volume-weighted averages type of calculation, as far as the incrementals in the forecast cells are concerned, those numbers are going to be exactly the same, even though they're going to be exactly the same whether you do the accumulation in a horizontal fashion from left to right or whether you do the accumulation in a vertical fashion from top to bottom. So that means that if I do it from left to right, but I do it with the original data first and then with the transposed data, then the incrementals I'll get in my forecast table in the transposed array, for the transposed array, will be precisely the transpose of the incrementals in the forecast for the original array. So those numbers are in fact the same, and there's a good simple reason why the means add up to exactly the same amount. So if you're conducting the deterministic chain ladder, you'll have no problems there. However, when you're doing the MAC chain ladder, we're also adding a regression calculation. And the regression calculation does come out differently depending on whether you do it from left to right or from top to bottom. And the reason for that is that those regressions are conditional on, for doing the standard MAC, the regression is conditional on the first development period. The first development period isn't estimated, it's used as the basis for all the other estimations. So it forms a starting point. But the starting point when you're doing the transpose is different from the starting point when you're doing the original data, because the first development vertical is different in the two cases. So even though you get the same means, you're starting from different numbers, and so the regressions are going to produce different estimates for the standard deviation. And so that's an equivocation that you can find in MAC. I mean, there's really no reason to prefer horizontal over vertical. In a way, you might as well just choose, whichever gives you the standard deviation you're happiest with. But in a way, they're equally random. So in this case, it's a little bit of a drawback to the method that it is so radically symmetric between the horizontal